Let's talk for just a minute about, first of all, what is fan pressure and why is it important to our DuctQuote design? Why is it important just to ducting design? Well, duct is, especially industrial ventilation ducting, it's designed to allow air to move, and it's got to move it at high enough velocity to maintain whatever it is that you're removing, the waste, particles, dust, whatever. It's got to maintain that in the airstream, which means we've got to have enough velocity to do that. Now, fan pressure is simply how hard that fan has to pull to keep the air moving at that target velocity that we have in the duct system. Now, it's kind of obvious, but fans that are working harder, pulling harder, use more energy, higher power bills, and they wear out faster. So it's important for us to, we're going to say, optimize our fan pressures versus our flows, okay? So again, why is it we want to minimize those pressure requirements? Well, like we said, fans that work harder, they use more energy, more power bills, and they wear out faster. But lower pressure, well, it can mean that the airflow is moving easier at a given velocity, but that's very important. The velocity has to be within the target range to move whatever you are trying to move through the ductwork. And to stay at that given velocity, that's what's going to give you that better removal or collection of whatever the waste is that you're removing, okay? So you have to balance the velocity with the fan pressure. They have to be optimized. So how can the trunk routing impact fan pressure? Well, typically the straighter the path, the lower the fan pressure, given everything else being the same. But let's hop in and take a look at some of this. So we're going to load up DuctQuote, and I'm going to open up one of my training projects here. Okay. So let's take a look at something that I see fairly often, where we've got a collector over here, and we've got duct that's going to pick up row after row of machines, okay? Now, we can do this in several ways. Now, typically we think the straighter the path along the trunk, again, the lower the fan pressure. But we also have to remember that more branches equals more fan pressure. And what do we mean by branches? Well, most people understand that. And let's just get that. There we go. All right. That if I have duct that stops here to run down and pick that up, and then we stop here to run down and pick up this line, and we'll run one more out, and we'll run down, pick up this line, okay? So we have branches, and we have an elbow, right? Now, if we look at the pressure requirements here, and I'm just going to leave them the same so we don't change the size of anything, right? And we're going to calculate. So here we have our total CFM, and wow, 18.5 inches of water column. Well, sometimes the straight line, because if you think about it, this is straight and in, straight and in, straight and in. Sometimes that's not the best. So let's take a look here and see what else might be. Remember I said that branches can also have a big impact. So let's again run down and pick this up. But now we're going to run over and we'll run back up to pick this up. And then we'll run over and pick this up. Now, this is a situation where we needed no branches to reach all of the machines, but we do have elbows. So keeping everything again the same, Wow, that's a huge difference. So let's talk about really quickly why that's such a huge difference. So here's the difference where we have, and I'm going to actually create a branch here. We're just going to stick one on right there. And let's zoom in for a minute, okay? So here's what's happening in an elbow. We're simply taking the air and we're turning it to move in a new direction. And by the way, this is a 90-degree elbow. The lower the degrees, say a 30 degree, there'd be even less pressure loss or fan pressure required for a 30-degree elbow than a 90 because we're turning it hard. And what really causes that fan pressure is when the air starts to tumble, or what we call turbulence, okay? So why is that different than something like this, which is a branch? Well, we've still got air coming here, and then we are shooting air into that, which disrupts not only this airstream, but also the main airstream as well, okay? So that is one of the big issues that cause that fan pressure to be higher. And again, we talked a little bit about the radius, and that is the rate of turn. Now I want you to watch for just a second. Here I'm going to select, and we can see that there's a 1.5 D elbow. If I were to make that a 1 times D, or 1 times diameter, that's a much sharper turn. This would require higher fan pressure. If we go to a 2.5 D, that's a much slower turn and much less turbulence, therefore less fan pressure. The problem is this takes up a lot more space, right? So that is why we choose kind of a middle of the road as our standard of a 1.5 D. So keep in mind, we want to look at things like the radius of our elbows. Do we need a short, sharp turn? In other words, 1 times D, or can we live with a 1.5, or do we need something like a 2.5, a much longer radius? Lower degrees of turn in those elbows also show lower fan pressure, okay? And also there are some folks who, and let's kind of do this. Let's go ahead and just redo a little bit. We're going to quickly draw a little duct, okay? And we're going to create a branch, just like that, okay? Now, this time I'm going to allow it to increase this, because the other thing that we need to think about is tapered trunks. So as we add more air from these two streams, this needs to get larger to keep the velocity the same. So this time I'm going to allow DuctQuote to change the size when we calculate the pressure. So here we go. And we can see that this is a 2.1 about fan pressure requirement. And that is a 45-degree branch with a 45-degree elbow. Now we also have the ability to come here and say, no, we want a 30-degree branch, okay? But that would require a 60-degree elbow to make that right angle turn. So let's go ahead and create that as a 30. Now, yes, a 30-degree branch is going to have less fan pressure requirements, or what most people call pressure loss. So when we calculate again, we had 2.1 before, we've got about 2.1 again. The difference is way out here in that third digit after the decimal point, okay? It was a 0.125 for the 45 with 45. The 30 with 60 is a 0.128. It's a very small difference, but that 60-degree elbow turning makes a difference, okay? All right, so talking about tapered mains, let's talk about what could happen. So if we have, let's say and let's kind of take that branch out, and we're going to change a few things here. We're going to take that back to 18, right? And we'll just say this is just going to be a floating point. Now, let's make that 18 as well. All right. So we've got 18-inch duct. If we wanted to bring things into this, right? So let's say we've got a whole series of 6-inch connections. And we'll put several in here. Okay. Now, we've got an 18-inch maintained the entire length. And I see this fairly often with folks who think that it will be a great way to save money because they've already got, let's say in this case, 18-inch duct, and they're going to reuse it for the entire trunk. Okay, so I have not allowed DuctQuote to change that 18-inch trunk. If we calculate, we can see that we come up with just under a 4, 3.8 about, okay, inches water column required for the fan. Well, what happens if we actually are putting 6-inch into all of this, right? And just to kind of prove a point, let's do this. Let's remove this. We're going to do this again. I'm just going to make that an elbow. Okay. So let's run that again. And it gets a little bit lower because of the branch going away, 1.9. So we'll call it about 2. But if we allow this to be optimized by allowing DuctQuote to change it, 1.9, but look at this. We're much better at maintaining our velocity. There it goes, 2.3, because this has gotten lower. But again, let's look at our velocities. Much better at maintaining our velocities here, okay? Otherwise, when, let's say right here, which should be an 8, if it's an 18, when this air comes in, it slows way down, as you saw, down to like 1500, which means a lot of the particles are going to drop out. Now, it's not such a big deal if the entire system is collecting nothing but fumes, but it can be a very big deal if you're collecting, say, sawdust, which is flammable, which builds up if it precipitates out in the duct, okay? So that's the concept of a tapered trunk that slowly gets larger as we add more air so that we maintain that velocity, as opposed to running one long, huge trunk where everything that comes in, you end up with a little pile of stuff right after the branch, okay? All right, so last thing, let's close out of this. It has to do with branches, double branches and single branches. Now, double branches are very convenient for installers, but they can be a problem if you have lots and lots of them. And one of the big things to understand, this is system 2 and this is system 1. When we run the calculation, okay, we're going to keep it just like it is so it can't play around with things. System 2, 3.25 essentially, but system 1 is 2.83, significantly lower. Well, what is the difference? The only difference is we've mismatched what's coming in. So we've got a big airstream coming in there, fairly large coming in here, but then we're shooting this tight little 4-inch straight into it all and really causes a lot of turbulence. Whereas here we've got the same 2 coming in, but if we move that 4-inch to its own branch, which is a little bit downstream, and it's really not that far downstream, we're talking less than 3 feet. It makes that big of a difference. So try to avoid mismatched sizes in your double branches, okay? That can save you fan pressure. All right, so to kind of cover what we have just talked about, fan pressure is important because it has to do with how easy it is to move the air, how hard the fan has to work to move it. Fan works harder, wears out sooner, needs more maintenance, and chews up more energy. Well, how does the trunk routing impact? Well, basically, the straighter the path from whatever to the collector or fan, the better. The more branches is going to equal more fan pressure required. Typically more turns and elbows, same thing, but they are much less of a turbulence causer than branches. And another good idea is think about moving the air always quote unquote forward, meaning towards the fan or collector. Try not to make it go backwards because that means the fan has to pull it away from itself essentially. Now, elbows, its radius, longer radius, lower fan pressure, but uses up more space. The degrees on both elbows and branches, lower the degree, lower the fan pressure requirement. Just remember that if you're trying to make a right-hand turn, a 30-degree branch is still going to need a 60-degree elbow to get it into the right-hand turn. And don't ever, if you can avoid it, mismatch the size on double branches like what you saw there, which was a 24, 18, 16, 4. Move that small 4 into its own single branch, okay? And then finally, use tapered trunks. What you save in power and cleaning out and maintenance of the system is probably going to more than pay for the duct if you've got duct to reuse. All right. Well, we have pretty much reached the end of our lesson today. So I want to thank everybody and invite you to keep an eye out for the announcement of next month's webinars, and wish you all a great rest of the week and a wonderful weekend.